Having a little trouble getting back to where I can turn on the video.
Hey, it was on, but you turn it off, so you have to go.
Let me stop sharing,
Yeah.
turn my video on,
But
and I can go back.
yeah, meanwhile, let me start introducing you. So it's 1 p.m., so it's time to start our colloquium and webinar. Yeah, it works now, so you can start sharing your screen as of now. So today we have a talk by Rick DeVore, and he received a physics degree from the University of Louisville and astrophysical sciences degrees from Princeton University. He began his working career in 1981 as a research physicist at the Naval Research Laboratory for Computational Physics, and then transitioned to Goddard Space Flight Center's Space Weather Laboratory in 2013. Among other recognitions, he is a fellow of the American Physical Society for contributions to computational MHD, and he received a NASA Exceptional Scientific Achievements Medal for advancing understanding of solar eruptions. So, Rick, you have your 45 minutes. I will give you 5 minutes warning before the end of your talk. So please go ahead.
Okay, that's great. Thank you very much for that introduction, Gregory. I appreciate it, and for the invitation to participate today and tell you a little bit about work that I have done with many colleagues, as you will find as we go along here. And so I'm going to tell you, as Gregory said, about adaptively refined MHD solutions of solar eruptive events, or SEEs, as they are commonly known. So here's an outline of my talk. So I'll start with a little general background to set the stage for the work that I'll talk about. And most of my talk will be broken into two parts. The first part will be about numerics, where I'll tell you a little bit about our adaptively refined MHD solver, or ARMS code. This is all going to be high level, so don't scurry away because you're concerned I'll throw a lot of finite difference or finite volume formulas at you. Then the second major part will be about the physics of SEEs. I'm going to focus on just one example calculation that we've done, which illustrates a lot of the principles and which is of current interest given Parker Solar Probe results and so forth. And then I'll give a few brief remarks about prospects, including collaborations that we are happy to engage in, willing to host. And then I'll close with some acknowledgments of a host of colleagues with whom I have worked and who have suffered with me through many of these numerical developments over the years. So with that, let me get started. This is a Solar Dynamics Observatory movie of an erupting solar prominence, seen here in the lower left or southeast quadrant of the sun. The sun launches these eruptions on a regular basis, as we well know. Let me start that again. So we see this large filament here in the lower left quadrant, the dark structure that begins to rise slowly and then erupts, suddenly transitions to a very fast expansion and escape from the sun, and leaves behind this bright arcade of solar loops behind it, which we know as the flare arcade, and it's delineated by these two bright ribbons, which we know as the flare ribbons. Let me show you a more close-in view of the same event, so you can see the filament there erupting. You can see a lot of twisting or untwisting of the magnetic field that occurs there, and the cool material, the dark absorbing material on the prominence gets spread around as a result, and then the bright flare arcade is left behind. So these eruptions are of interest scientifically, just as a solar physics or astrophysics problem, but as you all, I'm sure, know, they have very great impacts on our terrestrial environment as well through space weather. And so this artist's conception of sort of the heliophysics space weather system illustrates this. So at the left side, we have a erupting prominence and flare like you just saw in the movie, pointed out by the arrow occurring here in the sun's northwest quadrant. And what transpires from with time delays of only minutes in the case of electromagnetic radiation to a few days in terms of the plasma fluxrope and its magnetic field, its magnetic clouds, bring radiation storms, particle storms, magnetic clouds, and geomagnetic storms to the Earth if the Earth happens to be in the path of the eruption. And these pose hazards to technology on the ground. They pose hazards to technology in orbit. There are spacecraft. And if we have astronauts up there, especially if we have Artemis astronauts out beyond the protective magnetosphere of the Earth, then the astronauts personnel are also facing hazards as a result of these storms. In addition to these large storms, though, if you look here in the upper left, it's very hard to see. I'll show you a much closer image of tiny jets at the sun's poles. These have very minor space weather consequences as we see them at Earth, but what we've learned over the past half decade or so is that the same mechanisms that are responsible for the very large prominence eruptions and major flares seem to also work for these tiny little jets that are happening much more frequently over in much more numerous regions at the sun's poles. And so we can focus on those, which we can resolve better numerically, although we can't resolve them as well observationally in doing our numerical studies and trying to understand what these mechanisms are, how they work, and what their consequences are. So with that, I'd like to go and start my description of the numerical modeling. So as I mentioned, we use a code now that we call ARMS, the Adaptively Refined MHD Solver. ARMS solves a time-dependent MHD equations. It can be configured at compile time to run in 2 or 3 spatial dimensions. Two-dimensional calculations are highly idealized, but their advantage is that they can be very highly resolved compared to the 3D calculations that we are able to do. And that can be helpful in many situations, although they are less realistic because they are so idealized. The code will run in sorry, I heard some sound coming from out there. The code will run in Cartesian, cylindrical, or spherical coordinates. This can be determined and set at runtime. Basically, the code is set up to use metric factors that can be chosen at runtime to solve whatever problem that you wish to address. The code uses a finite volume representation of the magnetoplasma. And so it's a fairly straightforward computational fluid dynamics representation for hydrodynamics. And I'll show you some more details of that in just a moment through a geometric figure of our grid. And one of the major strengths of our code is that it uses adaptive mesh refinement. So the grid is not fixed to be structured the same resolution everywhere or with some fixed stretching that's true everywhere. Instead, the grid can be refined in very localized regions according to any criteria that you wish to specify that the code currently accommodates, which can be gradients of scalars, it can be electric current. We also have methodologies for pre-adapting the grid to particular configuration so that we ensure that we have high resolution everywhere that we think we will need it during the run. So these are the MHD equations. They should look fairly familiar to you. The first 3 represent the plasma quantities. The last, of course, is the induction equation for the magnetic field. To get a finite volume representation, you can imagine for the 3 plasma equations, multiplying by a differential volume element and then integrating the equations over that small element, whether it's a cube in Cartesian coordinates or a little cylindrical wedge or a spherical wedge in the other two coordinate systems, then you end up with, then the leftmost term is just the time rate of change of the corresponding integrated quantity, mass, momentum, or energy in that cell. The divergence terms integrate into differences of terms on the faces of the cells, which have area factors on them. And then the other source terms integrate in various ways depending upon their specific mathematical structure. The induction equation is only slightly different in that magnetic flux is the quantity that's conserved, so it's an area-centric quantity rather than a volume-centric quantity like mass or momentum or energy. And so for the induction equation, we integrate that over an area of a cell, and that converts the first term into a rate of change of magnetic flux through a face. And the curl terms then turn into line integrals around the perimeter of that face and involve length metric factors along with the specific information that's in the electric field, whether it's the ideal induction electric field, V cross B, or the resistive eta curl B term on the right side. So this is what the representation looks like in finite volume. So on the left is the fluid quantity. So we have, say, mass density defined on that cell. It's got an average value over the cell. And when we do that finite volume integration, we have fluxes through the 6 faces. And this is a flux conserving formulation because, for example, the flux of mass density through that top plane will just exit the cube that's shown in the figure and enter the grid cell just above it. And so it's conserved, except that at the boundaries of the system, you may have outflows or inflows that modify whether the total mass of the system is conserved or not. Likewise with the momentum and energy. The right side shows the magnetic field. The field components are staggered to the cell faces. And as a consequence of this, the fluxes then are calculated as area integrals of those factors, multiplication of an area times the field component. And they change due to the electric fields. They're evaluated along the 12 edges of the cell, such as the one on the nearest front right edge, the vertical edge. And that electric field modifies both the field component to the left, facing in our direction, and the component to the right that's facing to the right in the figure. And the contribution comes with equal magnitude, of course, but opposite sign. And so what that means is that any flux change due to that electric field that's introduced on the front face will be exactly balanced by an equal and opposite change on the right side face. So it's like the magnetic field is just sweeping around the corner in one direction or the other due to the flow velocity or due to the effect of the electrical resistivity. So if you think about integrating Gauss's law, div B is 0 over this cell, that reduces to a sum of the 6 face fluxes, and that sum is conserved in principle to machine precision because all of these electric field fluxes change 2 of the surface fluxes by equal and opposite amounts. So that's the representation that we use. This was basically realized by several investigators independently at about the same time and has been very widely adopted in a number of numerical MHD codes ever since. So I'd like to take just a couple of minutes, just a couple of minutes and talk a little bit about our flow solver. Because after all, the flow solver, the convection solver, is the heart of any magnetohydrodynamic code. In our case, we use flux-corrected transport. FCT was invented at NREL by Jay Boris, initially for 1D hydrodynamics problems, in particular shock waves and blast waves. And it was the first monotone scheme, so-called monotone scheme for fluid equations. It was followed by others like the essential non-oscillatory method, the piecewise parabolic method, Godunov schemes for Riemann problems, and so forth. After that initial development, the scheme was elaborated and extended to various finite volume algorithms by David Book and also by Steve Salazak. And Steve also developed the multidimensional extension of flux corrected transport of FCT, how to do it for hydrodynamics in multi-dimensions, which can better handle such problems as incompressible flows. Compared to the standard approach at the time, which was to do a direction split integration, where you'd integrate first along, say, X and then Y, and perhaps even then reverse the order and do an averaging to try to avoid any biasing in the solution. Instead, he's recommended and explored how to do fully multidimensional solutions from the outset. Now, if you recall the figure of the grid for that I showed, in the case of MHD, that's you basically have to do the problem really multidimensionally, because any electric field component affects magnetic field components due to gradients along two directions and affects magnetic fields in two directions all at the same time. And so it simply was seemed to be the most logical solution to take, was to make that solver fully multidimensional and to adopt a corresponding multidimensional solver for the plasma. And so that's what I did at the time, was figured out how to do the induction equation part, the MHD part of that development, that extension. What I'd like to point out about FCT is that it was early, it was very effective, and I'd like to point out that in its development, the emphasis was not on theoretical orders of errors or accuracy and finite difference expansions. Instead, it was on emphasizing the positivity and the monotonicity of the solutions. After all, when you advect the plasma density, even at a shock wave, it's always positive. Mass density is always positive. And you prefer not to introduce numerical errors in the form of ripples in the solution. If you think about trying to represent a step function with an increasingly high order polynomial, what you're going to get is increasing numbers of ripples of increasing magnitude. And that can work against both your positivity and your monotonicity requirements and properties. And because of that emphasis, the typical schemes for FCT are not that high order. Typical schemes are second order in time and fourth order in space. And they do quite a good job, especially at handling shock waves, in particular a step function. May start out as an idealized discontinuity, but will spread over about 3 grid cells as it propagates across a grid. But then it will simply propagate essentially unchanged after that, without any further spreading of the front. And we see that also actually in our MHD calculations, where we form current sheets, which if you think about it, are simply step functions in the transverse magnetic field. And so as long as the current sheet is evolving fairly slowly, that discontinuity can be maintained at the grid scale for quite a long time until, for example, there's some strong compressing flows that drive the field together at the current sheet and force the reconnection. And we do see that in some of our simulations, as I will show you in just a few minutes. The paramesh is the second key part of our package. In addition to the FCT algorithm, paramesh stands for Parallel Adaptive Mesh Toolkit. This was developed at Goddard by Peter McNeice and Kevin Olson and collaborators. This was supported by a very forward-looking NASA program at the time, High Performance Computing and Communications for Earth and Space Sciences. This was at the time of the advent of cluster commodity processors using fast networks and message passing interface communications, which were starting to replace the vector computers that had been so prevalent before, especially the Cray computers, simply because the commodity processors were so much cheaper. So NASA made this investment, which has had far-reaching implications and made possible a lot of progress in our field. It supported further development of our own 3D fixed grid FCT code. It also supported the development of Paramesh, which became the backbone for ARMS, but Paramesh also is the backbone for the Flash, astrophysics and thermonuclear detonation code, and for many other models as well. And there's a lot packed into this last sentence. Paramesh parallelizes and manages the block adaptive grid data. That is a huge task. It's a very complex task, and I applaud Peter and Kevin for taking that on and their development of it, because it's been extremely valuable to us and to many other investigators over the years. So just to circle back, so ARMS is the adaptively refined MHD solver, as I mentioned. Our fixed grid 3D FCT code we developed, Paramesh was developed, we put them together. We were supported in doing this by a Department of Defense software program, the Common High Performance Computing Software Support Initiative, which was similarly targeting development of software for the new growing class of cluster computers. The code was developed at NRL initially while I was there, and then transitioned later to Goddard when I moved over. I wanted to call out Spiro Antiojos in particular here, because Spiro pushed really hard for the development of ARMS. So he conceived our SESI software project, he led that, and he even gave ARMS its name, the Adaptively Refined MHD Solver, because of course, what DoD person could not like a software package named ARMS? So now what I'd like to do, that's all I'm going to say about the numerics. I'm going to turn now to discussing more about the physics of jets. So this is a movie from Hinode from many years ago now, but what you can see here are all these little bright points here in this north coronal hole of the sun. They're brightening up. Occasionally you'll see a jet. There goes a jet from near this center. I'll see if I can get this to play again. Brightening up, sending jets out into the heliosphere. And as I mentioned earlier, there's evidence now that although they're very small and energies are much less, they are very numerous, and the jets seem to have mechanisms that are very similar, even identical to those that drive the much larger space weather effective CMEs and flares that we saw before. So here is a higher resolution SDO movie in several different wavelengths of a jet from my colleague Pankaj Kumar at NASA Goddard, showing the development of activity in a jet in a small region of a coronal hole. You can see here the activity's building up, and then there's a sudden transition, brightening of the plasma and escape of a twisting helical jet into the outer corona. So we have been exploring models for quite a few years for how these jets work. This figure is a very idealized picture of the configuration. What we find is that these jets are all centered on minority polarity concentrations of magnetic flux in the majority polarity C of the coronal hole. In this case, the background is in red. Pardon me. And the minority polarity here is concentrated in the center inside this polarity inversion line, which is the black dashed line. All of the magnetic field the flux emanating from this minority polarity closes down to the surface nearby and forms this sort of dome-shaped configuration of closed field, indicated by the blue field lines, surrounded by the increasingly straight background coronal hole field lines farther away. And near the dome, the coronal hole field lines drape over the top of the dome. And at the top of the dome, here between the two flux systems, between the closed flux in the blue and the open flux in the white, is a coronal null point. So we took that same configuration. The previous calculation, I should have said, was done in Cartesian coordinates, in dimensionless units, and without gravity. But it showed the basic principles and basic operation of the mechanism. So in this subsequent calculation that Judy Carpin led, we adopted the similar configuration, but in spherical geometry. We put dimensional units on everything. We included gravity, which meant we also had to include a wind. We used a simple isothermal model for this calculation. And as in that earlier work, we then energized this field. This initial field here is potential, so it has no excess energy stored in it whatsoever, by introducing a slow rotational flow here around the interior of the minority polarity, which gradually twists the field and adds shear and adds excess energy to the field. The little nodule up here is a surface of high beta, which encloses the magnetic null point. And so as that motion starts, it's very slow. I'll show a movie of this in just a moment. As the motion progresses, the twist builds up over time. The field becomes increasingly twisted, and the addition of this twist adds this new azimuthal component of magnetic field, which increases the magnetic pressure within the dome and causes the dome to expand. And the easiest direction for it to expand is upward, and so it gets taller and taller as the calculation goes on. At this terminal time that's shown in this plot, there are about 1.5 turns of twist that have been introduced to this field. You can see it's very highly twisted. There's quite a significant amount of excess energy stored in there. But what I would like to point out is that the field has remained contained, the twist field has remained contained within the dome through all this evolution. So despite the fact that the null point has gotten distorted, there's been this slow motion upward, the twist has remained contained inside and the outside field has remained undisturbed. So
Can you just a clarifying question is what's the profile of the twist you're using? Is it vary with radius up in a uniform way, or is it discontinuous from the middle to the outer edge, or what?
no, it's continuous. It's actually a solid body rotation in the center, and then it falls off smoothly to zero toward the edge.
Good, thank you.
Okay. Okay. So then, subsequently though, let me go back here. So at this point, you can see in this last figure here in the lower right that the null point structure, which is a constant beta isosurface, high beta isosurface, is starting to be significantly distorted into fragment. And that's because the dome has gotten so tall that it's now about to topple. And this is an ideal MHD kind of instability, right, that has come on because the dome has gotten so tall. But what happens is when it topples over, it then drives this twisted magnetic field against the null point. And at that point, then that drives the twisted field through the null and into the untwisted straight field outside. And that initiates fast and energetic reconnection. That fragments the null point and develops a very long fragmented current sheet here, which then precesses around the dome at the surface of the dome as basically the twisted field inside gets transferred to field, the twist inside gets transferred to field outside. And when the field outside is reconnected with those twisted fields, it has a sharp bend on it, but its far end out in the heliosphere is unconstrained, so it can relieve that twist simply by straightening out. And so that causes the field lines to whip around, driving large amplitude nonlinear Alfvén waves along the field. And most of that outer twist, you can see here at the last frame in the bottom right, most of that outer twist is now gone. It's been transferred to the external field and it's propagated out into the outer corona. The most low-lying fields still have some significant twist on them because they are embedded so deeply in the region that they can't reach through the current sheet to relieve their stress. And now the ideal MHD impulse is subsiding because most of that excess energy inside has now been released. So this is a movie that shows the evolution low in the corona. I would like to say that the our motion here is subsonic, so it's quite slow, much slower than the Alfvén speed in the surrounding corona and coronal hole, and you can see the untwisting there and the propagation away of the Alfvén waves after the reconnection gets underway. So slow evolution, gradual rise, and then suddenly everything turns loose.
Are you really saying that there's no fast mode shocks that come out with this thing too?
There are probably fast mode shocks that propagate across the field. But it appears that the flows that come out of the jet itself and that propagate out along the field lines because they are propagating parallel to the field are nonlinear Alfvén waves. Well, here are some views of the plasma velocity shaded against the plane of the sky at various times after the jet has started. And I have a movie of this also, which we'll show in the next frame. And here it is. The initial development is very slow because we're seeing the very gradual rise and low amplitude motions of the twisting until the jet itself turns off, at which point then there we go. Until the jet is launched onto the external field lines and then propagates rapidly away at the Alfvén speed. And I have a plot later that will compare the location of the wavefront with the time delay expected for propagating Alfvén wave. Okay. So first I'll show, before I get to that, I'll show an example of our adaptive gridding during this calculation. One thing I'd like to point out, these are two plots of the log of the mass density, but the scale changes. So please don't be confused by the location of this cyan boundary between the dark blue and the light green. They're at different heights, very different heights in the two panels. So at the left, we show our initial grid, which is designed to encompass the null point dome and a little extra volume around it. So that's very close to the surface, very low lying. On the right, this is very late. In fact, this is at the end of the calculation. And so you can see the dark blue contours there of dense plasma that have reached up quite high into the channel formed by the jet. And that's a dense plasma outflow that follows the Alfvén waves and flows out somewhat over the sound speed, much slower than the Alfvén speed of the leading front. But the grid has been adapted on the current density compared to the magnetic field, and that has been adapted there. The grid therefore has been adapted by in accordance with the currents that are generated by the Alfvén waves, and that's why the grid there is finely gridded throughout that large zone in the middle of the domain. Between the start of the calculation and the end, this grid had increased in magnitude by about a factor of 5 in terms of the number of grid blocks, number of grid cells. So to just show a few global quantities from this calculation. So this is the excess magnetic energy in blue and the excess kinetic energy in red. That is the two energies after subtracting off the initial values and the background quasi-steady state with the wind. So we have a steady buildup of magnetic energy after a slow ramp-up phase. The velocities are not turned on at high speed, but they're ramped up gradually and then held at fixed speed. And so that grows at a steady rate until the time we see reconnection onset. And immediately after that, the magnetic energy turns over and drops substantially. You can see that we transfer about 50% of the magnetic energy, or lose about 50% of the magnetic energy that's been stored by the motions during that time. And a large fraction of that has gone into the kinetic energy of the plasma, as you can see by the red curve, and its very steep rise after the start of the reconnection onset. And that energy is dominated by the energy that's in the Alfvén waves. I have not talked, I won't discuss any particulars about what magnetic helicity is, but if you know what magnetic helicity is, it's a quantitative measure of the linkages between flux systems. So it's a measure of the twist that's stored actually in this configuration. And the main thing I want to point out here is that we see this, the helicity build up as the twist develops, but we don't see any dissipation, any significant dissipation of the magnetic helicity once the reconnection turns on. The surface motions are continuing throughout this at a steady pace, so helicity continues to be injected even as the jet leaves and is long gone. But the trajectory, the slope of the helicity curve basically doesn't change at all. So we're not dissipating, destroying helicity as the jet propagates away. That's turned out to be very important for some of our other work, which I don't have time to talk about today, in the helicity condensation model. I promised to show a plot of the front of the leading Alfvén waves. Those are the data points where I've looked at specific time slices and identified where the front of the jet is located, the front of the Alfvén waves, and compared that with the solid curve, which is just a calculation of the time required for an Alfvén wave to propagate from the top of the dome to a particular radius based on the initial Alfvén wave profile. So it shows that our wave fronts are moving out at the Alfvén speed. In some subsequent analysis of this calculation, Vadim Uritsky did some analysis of turbulent exponents of the MHD fluctuations in the calculation, and also looked at the current structures and came up with this nice diagram that shows a 3-zone picture of our jet, which is, we have a leading edge, which has an immediate wake where we have these nonlinear shear Alfvén waves. At the bottom, there's a dense jet, which you saw in that grid plot that I showed, where the plasma was following much more slowly at about 1.5 times the sound speed. And in between, there's a transition region, which we call the remote wake. Now, we've taken that calculation, we extended it by going much farther into the heliosphere, and Merrill Roberts, a student working with Vadim, analyzed our results to make some predictions for Parker Solar Probe. And the point out the plus marks here that indicates the location of Parker Solar Probe in this particular trajectory that was used. And these are 3 time slices from our calculation showing the velocity magnitude against the plane of the sky. And so what he did was he took line plots out of these calculations. And this is for the immediate wake at the front of the jet. The key results, there are a lot of plots here, but the key results at the top, it shows the velocity magnitude, this pulse here at the leading edge of the Alfvén waves. Oh, sorry, my mistake. This introduces very large fluctuations in both the transverse magnetic field components and the transverse velocity components, which you can see here are quite similar in the 3rd and the 4th panels. And then here in the 2nd panel, we have a plot of the radiomagnetic field which is essentially uniform before and after, but is reduced in magnitude almost to zero. Actually, the background value is negative and reduces almost to zero as the field lines are whipped out of their initial configuration by these strong waves. And then they relax back and the original configuration is restored. So to summarize,
Rick, you have 5 more minutes to go.
5 more minutes? Okay.
Yeah.
All right. Thank you. Okay, let me go on then. Let me just summarize quickly then. So I've shown that the excess magnetic energy built up slowly in our region below the null point, and then when that twisted field below convulsed due to an ideal motion toppling of the dome that drove it through the null point, initiated the reconnection and launched the jet. We have nonlinear Alfvén waves that led that outflow and propagated away into the inner heliosphere of our calculation. The outflow seems to take the form of a switch on MHD shock wave, where there's a mild density jump, but there's a very strong transverse magnetic field and flow components, which are consistent with an ideal nonlinear Alfvén wave. And these properties are consistent with the Parker Solar Probe S-bins. There's a very simple configuration here without any declination in the magnetic field. Our initial field was strictly radial, and there's no solar rotation in this calculation. So it's sort of the worst to try to actually get a reversal of the radial field, but we almost got it in this calculation, and that probably justifies further investigation. So the calculation I just showed had very simple thermodynamics. I mentioned it was an isothermal model, so we can improve our understanding of plasma responses to solar eruptive events in general and jets in particular by adopting a more comprehensive treatment of the kernel thermodynamics, and that's in progress. As we get access to ever larger computer resources, we'll be able to do higher resolution and higher Lundquist number numerical studies. That's especially true in 3D, although it's true even in 2D. And finally, another frontier is one of the main focus points of the Sulfur project, which is coupled kinetic MHD models, which may be a K-arms model that can calculate energetic particle acceleration in events like this, where the particles and the fluid are calculated together. That's a possible target for future work. As far as collaborations, we are always interested in having prospective postdoctoral associates come and work with us at GSFC. Qualitatively new investigations that would be appropriate for a postdoc or for a graduate student typically require quite a significant investment of time and focus. So they tend to be rather extended 2-year to 4-year commitments. But subsequent investigations, though, by those that come and work with us and get trained, they can be independent and self-directed, or they can be collaborative or a mix. ARMS has gone out now to several organizations with investigators who have worked with us, and it's now hosted at those places, and work goes on with ARMS there as well as at Goddard. So I've mentioned some acknowledgments of programs already, so I won't belabor this other than to say recent work, mainly on the science, but also on the software, has been supported by NASA's Internal Scientist Funding Model program, which supports civil servant research primarily at Goddard. We're grateful for that. And now I'd like to turn to my acknowledgments. I've mentioned Spiro before, who's not only pushed for the development of ARMS, but of course has led many of our major science programs, solar terrestrial theory program, sun-earth connection theory program, etc., over many years. And he keeps coming up with these great theoretical concepts that just cry out for being tested with really complicated MHD simulations. So it's kept me busy for quite a long time now. I'd also like to acknowledge Judy Carpin. She's been involved in many of those science investigations on the application side, and she has long been the designated bug finder for ARMS. She's now relinquished that title due to her management responsibilities, but her contributions have been many and very much appreciated. The 5 people at the bottom were early colleagues of mine at NRL, from whom I learned about FCT in particular and parallel computing and how to do computational fluid dynamics. And I had a lot of great discussions with them about all of those topics and more back in the day. And then I have, as you can see, a long list of collaborators that Spiro and I have shared, mostly postdocs, a few graduate students who have worked with us on many different problems, far more than I could talk about even if I talked about strictly science applications for an hour. And I'm grateful to all of them too. And with that, I'll finish. Thank you.
Thanks, Rick. It was very nice presentation of really very ambitious, great project. So we are now open for questions and discussion. Please raise your hand. It will bring you on top of the participant list, and you will be then unmuted, and we'll have an opportunity to ask you a question.
Will you,
Yeah.
I'm sorry, Gregory, will you give me the questions from the chat, or should I look at the chat?
I propose that people who put questions to the chat then ask them orally, otherwise in the recordings they will be lost. So I propose to just articulate those questions from the chat.
Okay.
But now Chile.
Okay, thanks for the nice talk. Just a clarification question. You mentioned the Microsoft Pro's S bands. Do you refer to the switchback? Or something
Yes.
else?
Yes, the S-bends or the switchbacks, right?
Great, thank you.
Yes.
So this is actually a mechanism of producing a switchback by jets.
Yes, this is a mechanism. I mean, I've looked at the data and the characteristics of the not to the extent, of course, that the observers and data analysts have looked at, but my cursory examination, it looks like the fluctuations are very large amplitude Alfvén waves. They have a slight density enhancement associated with them. Now, one issue may be that this particular jet calculation I showed was from a fairly large region, and they're not expected to be that numerous, whereas Parker has seen the switchbacks or S-bends quite a lot. So one question is whether jets and even jetlets at much smaller physical scales and magnetic scales in the coronal holes would generate similar nonlinear waves that would propagate out into the heliosphere and be seen there. And that's, I think, an open question that's worth investigating.
Yeah, thank you.
Okay, other questions or from people who participated in the chat?
So Gregory, can I ask a question? I'm not sure.
Sure,
I
go ahead,
figure out
please,
quite
yeah.
how to raise
Mhm.
my hand with this.
Okay, you raise your voice. Yeah, go ahead.
Okay, fine. So I have a question about this helicity business. And
Okay.
you know, your plot that showed that continuing to rise was pretty surprising, actually, in many ways, I guess. And so I gather, okay, so you can, a couple of things. I assume from what you said that Alfvén waves themselves don't carry helicity. And a second question is, if you were to produce a flux rope in this simulation, for example, if you went to even much higher Lundquist number you had, and somehow you're able to produce a flux rope, would the flux rope carry helicity outwards?
Okay, let me see if I can address those. I saw sort of 2 parts of that question.
Yeah. Right.
I think the kink Alfvén waves, they do carry helicity out with them. And in fact, Etienne Pariat has done and reported simulations that he carried on, I think, after he had worked with us, where he measured the helicity that was leaving the top of, I think it was within the computational domain, but he put an artificial boundary in there and calculated helicity flux through that, and found that when the waves propagate through that boundary, they do take helicity with them.
So then why aren't you seeing a drop in the helicity
Oh,
simulation?
but there's no drop in the helicity here because the waves have not yet left the box.
Okay, so they haven't
okay.
left the box. That's the reason.
No, though they haven't left the box. This domain extended out to several solar radii, and I stopped the calculation before the jet got very close to the outer boundary.
Okay, that's clear.
Sorry, that's the clarification I needed
Yeah.
to issue. I see. And in other work with Peter Wiper, Peter has looked at different modified flux distributions at the surface. In this case, I had a concentrated minority polarity, but the majority polarity was all diffuse. He's looked at cases where there's a local concentration of both polarities as well as the diffuse majority polarity background. In that case, it's straightforward to get a filament channel to form between the two concentrated polarities and form a flux rope. And that flux rope definitely carries helicity. But what we find in that case, typically, is that when as the flux rope rises, it seems to undergo a transition to instability, which looks like it's probably also a kink instability, but perhaps it's torus instability. But that drives the flux rope through the null point. And then when the flux rope hits the outside untwisted field, then it reconnects and then transfers its twist to the external field, which then propagates away. So the flux rope again doesn't survive, but the twist, the helicity gets transferred to the external field and can propagate away.
So Jim, let me jump in here for a moment here. I think
Please.
Rick, what Jim is getting at is that if you were to put ultra high resolution at the null, so you get null point, where the currency forms and we have the breakout reconnection. If we were to put ultra high resolution there, then you'd probably get magnetic islands forming as part of the reconnection, right?
I think that probably would be true. Yes.
Because you do see them. Prakash saw them in the jets. These little islands. He saw them in the observations. And I have no doubt that you would get them. We would get them in the simulations. We have to put a lot of resolution though to get them.
Mm-hmm.
Now the question is, those islands that form at the jet currency, do they survive as they propagate upwards? It's not clear. But that's something we haven't done, Jim, because it hasn't been really an important issue to investigate. But it's something that one could do. It would just take a lot of resolution, that's all.
It would take a lot of resolution, but in principle, we could do that.
Yeah, it would not be a
But
big
keep in mind that if we're really serious about trying to produce energetic particles, I think there's, at least based on the modeling everybody has done so far on kinetics, we're not going to be able to get those energetic particles unless we have lots of islands, which means we're really going to have to do the best we can on the resolution to try to do that.
Right. So what Rick said before this is that when he puts in the twist in the form of a filament channel, so when he drives the system by creating a filament channel, then you get a different reconnection. You get the flare reconnection below, inside the close field region, underneath the escaping, let's say, filament channel. In that reconnection, which is very violent, we see a lot of violence, no doubt about that. Also, we put in a lot of effort to resolve that. What we haven't done is put a lot of effort into resolving the reconnection up above, because that generally is not expected to be as, energetic. We could do both. So we are doing exactly that. I mean, we're resolving the hell out of the flare reconnection. It's the breakout reconnection that we haven't put as much refinement on. But yeah, we could do a study, a kind of a focus study just on the breakout reconnection.
Mm-hmm.
Yeah, I think that does have value in the sense that, a lot of people have been looking for evidence of breakout on the basis of seeing energetic particles streaming down and, hitting the chromosphere at other locations and as signatures. And so, trying to, in the end, if we try to produce signatures by producing energetic particles, then that might be a good way of doing it.
Yep, the microwaves and so on will be the most sensitive indicator. And so we should definitely go after that.
Mhm. The only thing I would add to all of that is Jim, in our CME calculations, like our jet calculations with a filament channel, we do tend to resolve very well the flare current sheet, and that's where we do also see lots of islands, because that is very highly resolved. So we see islands that form at the breakout current sheet, but in our CME calculations as well. But out there's no guide field, and there's not a lot of energy that gets released as a result of that breakout reconnection above our CMEs. But it may be different for the jet, and that's definitely worth looking at.
Okay, other questions or comments? I saw one raised hand, but then it disappeared. I'm not sure. Okay, if there is any further questions or comments from listeners? Yeah, it looks like all possible questions. Hugh, you can ask question if you cannot raise hand for some reason. Just go ahead and unmute yourself. I can do so for you.
Hello, can you hear me?
Yeah.
Oh, okay. I didn't realize I could do that. So thank you. That was great. And I just had a specific question about implosion. I think that if you have a low beta eruption, you would have to have some sort of implosion to supply to balance the pressure, the magnetic pressure, and the gas pressure. So that implosion is easily observable in many flares, but maybe in a jet simulation like this with a high beta region, you don't have an implosion because somehow the presence of high beta makes it irrelevant, or how does that actually work?
Well, there's no high beta region in the jet calculation except right around the null point. The rest of the corona is low beta. Actually,
Okay. So
it's quite small. It's like a fraction of a percent actually at the surface
okay. So
in
in
the
that case, why does
minority
the energy
polarity.
conservation? Why would you not see an implosion, or do you see an implosion?
We've not seen any implosion, but certainly after the jet has departed, there is a relaxation and the dome collapses back to a much smaller size. But of course, there it's lost much of its twist field, and which generated magnetic pressure and caused the expansion in the first place.
Yeah. So that's simultaneous with the eruption, then that implosive motion.
Mhm.
Okay.
And what do you mean by implosion here? What exactly are you looking for?
Well,
Is
you
that
should.
that
in
the
the-
field drops back down to its potential state and
Yeah,
therefore
in the case of
squeeze
flares,
back-
you actually see inward motions of these large scale loops
Yeah.
as the flare reconnection, what you would call the flare reconnection happens,
Right.
and that's the result of the inflow, or a large scale inflow, and it's simultaneous with the eruptive motion of the CME itself.
Right. So one way to look at it is to say that the shear distress causes all the flux tubes to balloon outwards, to kind of minimize the magnetic energy. But once you get the eruption, either by the jet or by a CME, the field line now squeezes back down, dipolarizes back to its near potential state. We see exactly the same thing. I mean, Rick showed that in his simulation there. Before the jet, the field was bulged out like crazy when in this long tower, and then afterwards,
Right.
collapse, squeeze
Okay.
back down. So if you call that
Okay.
an implosion, yeah, definitely, it's there.
Okay, good. Thank you very much.
Mhm. And we certainly see that squeezing from the sides in our CME calculations. Once the ballooning flux rope has risen high enough, then we see compression from the sides, which helps really drive the flare current sheet together and supercharges the flare reconnection below. Thanks for your question.
Questions, comments? Yeah, no raised hand and no raised voice, and we are right on time. So likely I can finalize the webinar now. So Rick and all other listeners, thank you very much for being here today, and we will have next webinar roughly in 4 weeks from now, in mid of July. So thank you very much. Have a
Okay,
great
thank you,
summertime.
Gregory. Yes, thank you to everybody for attending. I appreciate it.
Thanks, Rick. It was very informative.